Let us explore the result of a Hertz contact stress analysis. Before we get started, we're going to start by looking at this from the Galactic subscription plan. So in the search bar, Hertz will get you directly to the calculator. We'll close that. The videos you already know. Now, in the reference panel, we'll give you 3 different references. The intro level, the practical engineering level, this is for someone already in the field, and the expert, which includes theory and practical. Now, one of the things that we'll have here is if we find any errors in the equations or comments, we actually put a little warning sticker. At this time, in the Galactic plan, which is more designed for a college level student or early career, you're not going to be able to see the details of this. So let's switch to a higher plan. We're going to switch it to the universe plan, which you take a lot more into account in a universe than a galaxy. If you go to the top, you'll notice that the color changed here in your plan, and that you have additional references, as well as you can click on the details of the warning, and it'll tell you this equation in this book has this actual sign error. If you go to the details of the other references, it also gives you additional references as well as their associated reference warnings. All right, so we're going to proceed with this plan, with the universe plan. Let's pre-configure. We're going to do a sample that we found in the Slocum book, which consists of a 3mm sphere on a flat, steel on steel, loading with 1 Newton. As you can see, all the fields are pre-populated. For a sphere, it's 3mm, so that means that the radius is 1.5 millimeters, flat. Let us start comparing against what the book states as the answer. The equivalent radius, what we are calculating to, is 0.75 millimeters. That agrees exactly with the book. For the material, equivalent Young's modulus, we are getting 111 gigapascals. The book for this just states that the equivalent Young's modulus is 110 gigapascals. So that depends a little bit on what the Young's modulus is and the Poisson. Given that they don't give us the details, we're going to minimize that and call it a day. And the loading is 1 Newton. So run it and explore the results. This is the circular contact area approximation. That is in one of the equations. And for that, we are calculating at 21.6. The book says 21.7 micrometers. For the deflection, we are calculating 0.31 micrometers. The book says it's 0.31 micrometers. So we're perfectly on target here. Because this is a circle, the major and minor radius are the same. Contact pressure, let's put it in megapascals. The contact pressure per the book is 1012, and what we have is 1018. That's perfectly reasonable. The contact stiffness, the way that we calculate it is by the axial force divided by the displacement. The book doesn't provide any information on that, but we do calculate the shear. So for the shear, put it in megapascals. We're calculating at 340 megapascals, 341. And the example in the book is 337. That's perfectly reasonable. Now, Let's move a little bit up and load up the second example, which consists of two cylinders, one cylinder having a radius of 0.4 meters, the other one having a radius of 0.3 meters. There's a 90-degree offset, steel on steel. In this one, they do provide a guidance for the material properties. We're going to have to change those a little bit. And the load is 90 kilonewtons. One of the things that you'll see the platform is throw you warnings of what the actual contact angle is in order to avoid misrepresentation. So you'll see that in the platform. That's what the warning was telling you, that for this configuration, it's going to set it as orthogonal 90 degrees and you cannot change it because we are looking at point contacts. There is another calculator where you can change this factor. Okay, let's change the Young's modulus to 210 and the Poisson to 0.3. One of the things you should be aware of, that when you have two materials that are the same, you can generate fretting, which is a failure mode of contacts. Let's run this, and based on the Yugoro example, it tells us that our major radius in millimeters is 6.46. We get exactly that. Our minor radius in millimeters is 5.35, and the book says 5.33. So we're perfect on that. And now let's go to the contact stress. And they put it in megapascals. We are calculating 1242. Per the book, it says 1248 megapascals. Part of the validation process for this calculator included comparing to 4 additional other Hertz contact analysis calculators. One of the things that was different is how do you calculate the depth of max shear? And the way that it's done, and this is how it's shown in Slocum's book, is via this equation. Beware, some sites just say that the approximation is 0.48 times the radius. That can lead you astray because it's going to go and give you a smaller depth of max shear, and this is particularly important in coatings, than what it may need to be. So default on the side of safety and actually use, it's around 0.633 for a Poisson value of around 0.3, but you can calculate it for different Poisson values using this equation. In addition, sometimes a calculator can be used to calculate a margin of safety. Now, because different industries put different numbers inside of the margins of safety, for example, it could be the yield stress, or is it the ultimate yield stress? Now, we actually calculate the margin of safety internally, and we can use the sigma ultimate, which we are not providing here, and because it can lead to a small typo and the impact is significant, we actually are not putting that in the calculator. The engineer will be responsible for using this information and finishing the last 5% of putting into the margin of safety for their organization. Like this video, subscribe. Until next time.